Everyone, welcome to SAT Math Question of the Day with Professor Emeritus Chaiken at the University of Albany and Seth's brother Joel. We're here to hopefully show you how to approach SAT math questions. Here we have yesterday. We're dealing these last 2 days with a question that has two questions. And yesterday we did question 21. Today we are doing question 22. We moved the chart away from wherever it was next to question 22, and today we do 22. Okay, so why don't you try doing it? Pause the video, and then we'll see you in a moment. Okay, question 22. Now that that's way, we have further that chart. It shows renewable energy consumption, BTUs by energy source. Okay, basically different types of fuels and how much they were used in over 2 years, 10 years apart.
2 years.
Okay, 2 years, 10 years apart. Of the following, which best approximates the percent decrease in consumption of wood power? So we only care about wood in the United States from 2000 to 2010. So it went down, right? The wood actually did go down. So there's a formula for percent decrease. It's the new minus original, okay, new minus original, divided by the original, I'm misspelling original, I hope that people don't mind, equals the percent P over 100. Okay, Seth's being very nice. He's writing it neater. So now we just have to put the numbers in, and then we're going to get a negative number, but these are positive numbers, but it's talking about a decrease. So it's okay if we get a negative number for this formula. So what is the new? The new is the new one, which is 2. The old one, which is 2 1/4. And the original is 2 1/4. So that's what we want. So, this is a calculator section. So let's just do it with a calculator, okay? And then we'll show you how to do it without a calculator.
Hold on. Oh, yes, wood.
It's
yeah.
2
That's
minus 2 1/4.
It's woods. This is the wood one. See, I saw there's a W for winds. It's really wood. So we look at this one.
Yeah. So it gets to be 11. The answer is.
So you got the 2 from here, and you got the 2 1/4. From here.
Right. So in a calculator, you get the answer is negative 0.111111111 P. So at this point, you should realize that the answer is 11%. But if you want to be stickler, you would then cross multiply solve for P, and you get minus 11.1% for P.
Okay, let's 2 minus 2 1/4.
It's a quarter.
Is a quarter, yeah. So we really should. So please write that is 0.25.
Yeah, but everyone has a calculator.
Divided by 2.25.
That's right, but everyone has a calculator. So you're gonna put that in. You don't.
But it's quicker to see. It's quicker to see that this is about a tenth.
Yeah.
This is about a tenth. The closest percentage that's about a tenth is B, so we could save time without using the calculator.
Exactly. That's right. There are two approaches. You could do that, or you could use a calculator. Thinking about whether you can do that takes time. So if your calculator's right next to you, you may just want to use it. People have to decide what they want to do. But this is a very important formula. And I don't know, would this be considered a formula or a relation? What do you think? Is that you call something like this?
Formulas are expressions of relations, and relations are expressible by formulas.
So it's
both.
Then it's both a relation and a formula. Okay. The common mistake everybody makes, and so many people make, is what do you divide this by? Do you divide this by the 2, or do you divide the difference by the 2, by the old, or by the new, or by the original? And so many people divide it by the wrong thing.
Yeah.
If you don't have,
well, it's by convention. It's divided by the original. You
right,
base it upon what it used to be.
right.
Right.
Yeah, so that's a very important thing to remember. We don't have to check it, although I virtually guarantee you that, well, should we just check it? What happens if you divide by 2? Well, that'll be, right? If you divide by 2, you
Still get approximately the same.
Really?
Yeah. It's only off. It's off. The percentage it's off is about 10%.
Well, you're right. It's 12.5%. Wow.
Yeah.
That's amazing. If you use the wrong number, you get 12.5%.
However, compare what happens if. Okay, that's not a good. You still absolutely need to memorize that when it asks for a percent decrease or percent increase, what you do is express as a percentage a fraction in which you divide the change by where it used to be, the original.
Right.
Now, if where it really matters is, say, if the change is 50%. Suppose something changes from 2 to 1. How much does it decrease?
From 2 to 1, 0.5.
Yeah. Now, what if you divide it by 1?
Yeah, you get what? You get 100%.
Get 100%.
You get 100%.
Yeah. So it's it's a difference between 100% and 50%. So it's absolutely wrong.
Right.
Yeah.
Yeah. So you have to divide by the original.
Yeah.
So there's not much to this, right?
Yeah. Now here's a tricky one.
Yeah.
Suppose you had $1,000 and you lost 50% of it. Right? Suppose you had $1,000 and you lost 50%. And now of the money you have left over, how much percent must it increase in order to get back your 1,000?
Yeah, no, the answer is not the same percent.
Is it 50%?
No, that's the
how much is it?
Question. Well, do you want me to actually do it?
Yeah, sure. To go from $500 to $1,000, how much percent increase is it?
Well, I'm a big fan of a formula that I named myself, which people I'm sure have seen other places, but I call it the shopping formula. Because when you go shopping, this formula is really, really helpful. Shopping formula. And this formula says that the new price when you go shopping is equal to the original price times 1 plus or minus D or P over 100. Should we say P over 100, the percent over 100? It's the decimal of the percent. So what was your question? So tell me your question again. What? How much do you have to go up if you want to go from 500 to 1,000?
Yeah.
Okay, fine. So I want my new price to be, hold on, Zyport froze. Our new price is going to be 1,000. Original price is going to be 500. We're going to solve for P. Okay?
Yeah.
Fine. So, Zyport froze. I'm sorry that we have to wait. Oh, okay, come on. There we go. Okay, so we want this to be 1,000. We want this to be 500. And we do 1 plus, I'm going to say D, where D is the decimal of the percent. Okay? So what we do here is we divide by 500. I'm trying to be neat. 500. And then we say 200. Oh, come on. Now the whole thing is going to go crazy. But it's 200. No, it's 2. It's 2. It's 2. 2 is equal to 1 plus D. So D equals 1. That's the decimal of the percent, which means that the answer P is 100%. It has to go up by 100% if it's going to go from 500 to 1,000. Am I right?
Yeah.
Right. Yeah. I love this formula. Why do I love this formula so much? Because this formula makes the hardest problem, one of the hardest problems you can get in percents, really, really easy. And what do you think the hardest problem is in percent questions? So,
okay, well, this formula is equivalent. You could write it a different way.
Okay.
New divided by original.
Okay.
Equals 1 plus P over 100.
It could be minus.
Plus or minus, where P equals where P percent equals the percent change.
Right.
Yeah.
So
and so notice whenever you have, we have here we have 50%. Okay, here's another thing to do. Converting between percent and ordinary numbers. Percent is just an abbreviation for 1 divided by 100.
Right.
So 50% is the same number as 50 divided by 100.
Yeah.
And that's the same number as 1/2.
And the same as 0.5.
Yeah.
So I can't resist the temptation to do what many people, certainly myself, finds is one of the most confusing questions out there in percents. And most people in 8th grade, in fact, everybody in 8th grade gets this question wrong the first time they see it. It's a guaranteed question to be wrong in 8th grade. Hopefully by the time you're in 10th or 11th grade, you're not getting this question wrong. But this is a great way to do it. Okay, you go shopping and you come home and you get a pair of shoes or a shirt or something for $35, and you're screaming, "This is the most amazing thing in the world! I paid $35 for it." And it was sold at a 70% discount. 70% discount. So then someone says to you, "Well, how much did it cost originally? What was the original cost? How much was the original tag? Before they marked it down?" And you say, "Well, I don't know. It certainly was more than $35, but I don't know what it was. I mean, how do I figure that out?" Well, with the shopping formula, it's extremely easy to figure it out. The new price, which is what you paid, the $35, is equal to the original price, which actually you don't know. So you call that X, and you got a 70% discount. So you do 1 minus 0.7. So now this is X times 0.3 equals 35. You divide by 0.3, and you get calculator time. 35, we don't need a calculator, but it's like 105, something like that. 35 divided by 0.3, what is it? No, it's 116. It's 116 and 2/3. Okay. Mm-hmm. So I use a calculator. I did 35 over 3/10. How come it's not? Anyway, let me do that again. 35 divided by 0.3 is $116. And then we can check, right? $116.67. Let's just make sure. 116 times 70% off means that you paid 30% of it. Yeah, right. Yeah. So that's it. That looks right. Okay, so this is a really tough question if you don't have this formula in your pocket. It is. It's easy to go the other way, right? If something costs $120 and you got you got 20% off, then it's 1 minus 0.2, so it's 80% of $120 is what you paid. The shopping formula also works that way too, but really, really helps in a problem like this. This is what I call the backwards question. We have to figure out the original. So, it's always helpful to keep the shopping formula in mind and use it for the backwards question, where you have to figure out what the original price is. So, anything else? Seth, that's right. Seth had an interesting thought. He was talking off camera before we started about thinking. and how to process math problems. And yeah, I mean, it's interesting that when you process a math problem, you sort of do it like you have to sort of think in parallel. Many people this age group are probably learning how to drive, and when you drive, you have to process a lot of information at the same time. Everything's coming at you at once, and you're paying attention. It's sort of like when you're doing math problems, many math problems. It's you sort of have to. I don't know where we are.
Mm.
Sometimes you feel like it's the same thing where you're thinking about the same problem at the same time in parallel through different ways, and it's sort of complicated. We can't really.
I don't know. Well, driving. You're like well, the only the if you when you if you ask the way I would answer if you ask is there similarity to driving and doing math problems, I would say that when you drive you encounter several different kinds of situations, and that you approach them differently. Like driving straight, on a highway, driving straight on a busy street, stopping at a stop sign or stopping at a red light, making a right turn when you have the right of way, making a right turn after a stop, going straight and approaching into a crosswalk. I think those are different situations that call you to bring to your mind different approaches.
Yeah.
And in math, when the problem comes into focus, you gradually or quickly begin to realize what kind of problem it is.
Right.
Yeah.
But as you're going through that and realizing what type of problem it is, you are at that point processing a lot of inputs. Like, do you do this graphically? Do you do this algebraically? What's going on?
But you don't consciously go through the list of possibilities.
But you don't do that when driving either. Once you have a little bit of experience.
Yeah, yes, that's right. You don't do that with driving. And when you do routine math questions, you don't do that either in math. However, one of the challenging things in math, and is especially when math is actually when math problems occur in real life as opposed to tests. The problem is most difficult when it's novel. That's not one that you could recognize as something that you know how to do.
Yeah. Well, we're not talking about that. We're talking about SAT math questions and standard math questions. But standard math questions usually on a test. If many tests, the question is just straight up the alley. It's just like a homework question, which in practice you know how to do. An SAT math question, sometimes you have to look at it like different facets, different views. And really, when you're doing that different view type thing, the brain is sort of doing it in parallel. You're not doing one view and then another view and then another view. I mean, to a certain extent you are, but you're also brain as you're figuring it out. You're like, wait a second, there's there's all this stuff going on. Which is really when you're driving, you got to process all the inputs at the same time because you don't have time to do every one. Anyway, is that an MIT mug?
Yes, it is.
Let me see that. I was able to figure that out. MIT.
Isn't
MIT
that
cool?
Mug. That's
Isn't that
right.
Cool? Wow.
It's cool. Really cool. It's a cool mug, and it's made by this artist. The artist is named Jean Plensa.
Yeah. Wow.
Jean Plensa.
Alchemist.
And it's titled The Alchemist.
Oh, wow.
Yeah, Alchemist, yeah.
Wow. There's a website.
It's full of Greek letters.
Wow.
Basically, all those, except for the 6. No, it's an upside down. It's an upside down row.
Hmm.
No. What's this thing? This is it's a 6,
I guess
and the
so.
rest are Greek letters.
The rest are Greek letters.
Yeah. Look. I looked up. Jean Plensa.
Yeah.
On the web, and he's a Latin American sculptor.
Oh wow!
Yeah.
Okay.
So usually his work is huge.
Wow. Anyway, it's a nice looking mug. Okay. Okay, everyone. Have a great day. Please like us, dislike us, give us comments, and so we can show you, hopefully give you some insights on how to approach. We don't know what the test is going to be like, but the approaches of these questions hopefully are universal for all questions. Okay, everyone. Have a great day.